Welcome everyone to lecture 4, the first segment. Today we're gonna apply general mole balance equation that we have derived in lecture 2 or 3, I believe, to the following two continuous flow systems: plug flow reactor and packed bed reactor. Let's start with plug flow tubular reactor. Tubular reactor consists of cylindrical pipes and is normally operated at steady state. As we mentioned, any continuous flow device or equipment, we would like to operate it under steady state to reduce, to minimize any disturbances or changes with time. It is used most often for gas phase reactions. And as you can see in these two pictures, here we have this is a bunch of tubes, right? So it's not one tube, bunch of cylindrical tubes with small diameter, or here we have one large cylindrical tube, large pipe. Plug flow tubular reactors. In the tubular reactor, the reactants are continually consumed as they flow down the length of the reactor. So here's our reactor, plug flow reactor, and we're introducing the feed at a rate of A naught. Okay, that's the reactant A, and as you can see, as the reaction mixture flows down the length of the reactor, A gets consumed, and therefore if you follow its molar flow rate, you can see the molar flow rate is decreasing for A, which most probably means the concentration is decreasing as well, which translate into most probably lower rate of reaction as the reaction mixture goes down the length of the reactor. Why is that? Let's assume we have an isothermal reaction where temperature is not changing. So here the rate of reaction will be a function of concentration of the reactant, and here the concentration of reactant is decreasing, therefore the rate of reaction is decreasing as well. Hence the reaction rate varies axially. So along the axis, the rate of reaction is changing, except of course for zero order reactions, where if they were run isothermally, so here the temperature is not changing, the concentration is changing, but the rate of reaction is not a function of concentration, so the rate remains constant. The fluid flow through the tubular reactor may be modeled as a flow of a series of infinitely thin coherent plugs, each with a uniform composition. So this is an assumption that we made, or a simplification that we made when we deal with plug flow reactor, where you have a reaction mixture flowing down the length of a tube. Okay, so the fluid flow, so I'm talking about the flow here that's going through the tubular reactor, whether it was plug flow reactor or a packed bed reactor, may be modeled as a flow of a series of infinitely thin coherent plugs. So you can see these are the plugs. Okay, these are the plugs, and they are very thin plugs, and one after the other. Okay, and then they are flowing, so the plugs are flowing. Okay, so this plug is here now. After half a second, this plug goes here, and this plug goes there, and this plug goes there, and so on. So the plugs are moving down the length of the reactor, and each has a uniform composition. So the composition throughout this plug is the same. Okay, the composition is the same throughout this plug. The same thing, the composition here is the same throughout this plug. But of course, it's different than the previous plug. For instance, you would know that the concentration of reactant A here will be less than the concentration of the reactant A here. So here CA is more than Ca here. So Ca here is more than Ca here, and so on. So as you know, the concentration decreases. Okay. The plugs are viewed to be traveling in the axial direction of the reactor, with each plug having a different composition from the ones before and after it. Let's look at this video. You can see that the plug started from the beginning and now it's flowing down the length of the reactor. Of course, in front of this moving plug there's another plug which is moving, and before it there's also another plug which is moving. So continuous movement of plugs, and hence we call it a plug flow reactor. As the plug flows down the reactor, the reaction takes place, resulting in an axial concentration gradient. The key assumption is that as a plug flows through a plug flow reactor, the fluid is perfectly mixed in the radial direction. The fluid is perfectly mixed. Use another color, maybe black. Okay, in this radial direction. The fluid is perfectly mixed in the radial direction, but not in the axial direction. So there is no forward mixing or backward mixing out of the plug into the other plugs. No, the plug is perfectly mixed in the radial direction, which means that the concentration here, the concentration here of A, for instance, the same as concentration of A here, the same as concentration of A here. The same thing goes for the temperature. Okay, but if you take the plug which is in front of it, another plug, the concentration here is different than the concentration there. What can each plug be modeled as? What type of a reactor? Batch or CSTR? So what do you think? Let's look at the plug. For each plug, is there any input or output? Is there any backward or forward mixing? Is there any? Of course not, right? So the plug is actually isolated when it comes to mass. There's no mass coming in, there's no mass leaving out, which means it's like a batch reactor, right? Especially that we said it is well mixed. Each plug is well mixed, which is again a property of a batch reactor. Okay, so each plug of differential volume. So each plug is very, very small, right? It has a differential volume. It's considered as a separate entity, effectively an infinitesimally small batch reactor, limiting to 0 volume. So actually, the smaller the plug is, if we model it with small plugs, the closer it gets to the batch reactor. Why is that? Imagine that we take a plug that is this large. Okay, let's take this plug here. It's very large. I know that the concentration of A here is much more than the concentration of A here. Correct? So now it's not perfectly mixed, right? Which is far from being a batch reactor. Okay, so but if the plug was very thin, I would know that the concentration at the beginning of the plug is almost the same as the concentration at the end of the plug. Therefore, you have a uniform concentration, also uniform temperature and uniform rate of reaction. Okay, so the smaller the volume is, the closer it is to the plug and the closer it is to the batch assumption. Plugs of reactants are continuously fed into the reactor. So as the flow continuously entering the reactor, as if I'm introducing new plugs. So this plug here will move on to there, right? And another plug is introduced now here. And now then this plug goes here, right? And another plug is introduced, and so on. And the plugs are just moving axially, right? Here we are looking at the flow. We are looking at the flow as small plugs. Great. Let's now look at the reactor. So we're not looking at the flow, we're looking at the reactor as small segments. So this is my reactor, and let's look at it as segments. Segment 1, 2, 3, 4, and 5. What can each segment be modeled as? What type of reactor? Batch or CSTR? Yep, think with me. Well, let's look at each segment, and you can see that there is a flow coming into each segment and flow leaving from each segment, correct? Flow coming into each segment and then leaving that segment, right? And we can assume that the volume of each plug is very small. If the volume of each plug was very small, so the concentration at the beginning would be same as the concentration at the end if the segment were very small. That means you have homogeneous solution here. The reaction mixture is homogeneous throughout the volume, so it's uniform. You have uniform composition, you have uniform temperature, therefore you have uniform rate of reaction, and then you have input and output. So this reminds you with a CSTR, correct? So plug flow reactor can also be viewed and modeled as large number of CSTRs in series. Large number of CSTRs in series. Why large? Because the larger number of CSTR, the smaller each segment will be, right? Smaller each segment will be, and then the closer it would be to the uniform, spatially uniform reaction mixture. Okay. Every segment which is infinitesimally small can be viewed as CSTR. And I said the smaller it is, the closer it is to the uniform composition, uniform temperature in each segment, and therefore it looks more similar to a CSTR. Okay, let's go to the plug flow reactor design equation. And let's start with the general mole balance equation. So input minus output plus generation equals accumulation within the whole reactor. So let's have our reactor and we do the design. We apply this equation on our reactor. So the plug flow reactor design equation can be derived from the general mole balance equation in two ways. Okay, the first way is from a mole balance on a species I in a differential segment of the reactor volume, delta V. Okay, so here, as you can see, we take a small differential volume. This is delta V. This is the small differential volume. Of course, here we are exaggerating. It's much smaller than this. Okay, and we do a mole balance on a species I on a differential segment of the reactor. So here, Shabab, the delta V is chosen sufficiently small such that there are no spatial variation in reaction rate within this volume. So again, the volume here is very small, so that the concentration of A at the beginning is same as the concentration of A at the end. The temperature here is the same as temperature here. Okay, so because we know if the segment was very large, if delta V was very large, we know that concentration of A here would be larger than the concentration of A here, and the temperature here could be different than the temperature here, but we take it as a very small differential volume. So again, it is the composition is uniform and the temperature is uniform throughout the whole delta V differential volume. So let's apply this and let's derive a design equation applying this approach. Right, so let's apply the general mole balance equation or apply the mole balance equation on this delta V. Okay, so let's see. This is the delta V here. Okay, starts here and ends up here. And input. The input to this differential volume obviously is Fi. It's not Fi naught, it's Fi, because Fi naught is here at the entrance. This is delta V is not at the entrance, so Fi. However, its value is found at V, at a general distance or volume V. Okay, that's the input. What about the output? The output is also Fi, however evaluated at V plus delta V, correct? Okay, input minus output plus generation. What's the generation? The number of moles generated per unit volume. Here, well, obviously we learned that the generation can be found from this integral RA times dV. However, now it's evaluated from V all the way to V plus delta V, correct? Equals accumulation, and the accumulation is for dNA over dt evaluated, of course, at this delta V, correct? Okay, so let's see. It's a plug flow reactor operated at steady state, so no accumulation, right? No accumulation. What else? Delta V is very small, so the rate of reaction is uniform throughout the volume. It's the same everywhere. Rate of reaction here, same rate of reaction here, same rate of reaction there, and so on. So we can take the rate of reaction outside the integral, right? So we have RA, and then the integration of dV is V, right? And it is evaluated from V to V plus delta V, and this equals to 0. If you allow me, I'll just switch here. I'll write Fi evaluated at V plus delta V minus Fi evaluated at V, but of course to keep it correct I have to put a negative there. Tamam. Okay, so let's continue. So now we have minus Fi evaluated at V plus delta V minus Fi evaluated at V, correct, equals R. Okay, sorry, if I used I, then I have to, the rate of reaction also has to be for species I. Okay, doesn't matter, we want to stick to I or A, but I started for the I, so everything should be I. Okay, times, what is, you have V evaluated V plus delta V minus V, so that will be delta V equals to 0. Now let's divide by delta V. Okay, let's divide by delta V. Divide by delta V. And this will take me to minus. Okay, if you allow me, Shabab, I'll write instead of Fi evaluated at V plus delta V minus Fi evaluated at V, I would simply write it as delta Fi, correct? That's what delta Fi is, correct? Divided by delta V plus Ri equals to 0. And now, let me put the negative closer. And now I'll take the limit. So take the limit, right, where delta V approaches to 0. Correct? Okay, what does this remind you with? Remember, Shabab, in math, you have discussed that how the dy by dx, right, the derivative, if we plot y versus x, and it is somewhere something like that, that dy by dx right, is simply the slope, right? It is simply the slope. So let's take, for example, the slope here. Okay, and in order to calculate the slope, of course, one would think, it's easy to calculate the slope. It is delta y divided by delta x, correct? However, I don't have a straight line here. I don't have a straight line. So, see, this is not a straight line. So, how are you going to calculate? It's not going to be correct if you take delta y and delta x, because if you take the values here and there, you will get different value than if you took the values here and there, right, for delta x and delta y. Okay, so when is it correct? When dy by dx equals actual delta y by delta x is when for the limit where delta x goes to 0. Delta x goes to 0. Is it clear, or maybe I should write it clearer? Okay, so let me try it. That's for the limit when delta x goes to 0. If the delta x is very small, very close, let me use another color probably. Okay, so if delta x is very, very small around this point, so if I want the slope here, if you want the slope here, then I'll take the delta x very, very small, very close to this. So obviously if I take the delta x is very small, the delta y will be very small as well, right? So here if I take delta y by delta x, then it indeed will equal the derivative, right? So if let's compare this definition to this definition, and you can see that therefore it can be written as, yes, minus dfi over dv. So I switch the algebraic equation to a differential equation, right? Okay, and therefore we can take the derivative to the other side, and you'll have dfi by, let me rewrite it, dfi by dv equals Ri, and now this is the design equation for plug flow reactor. Okay, so we derive the design equation for plug flow reactor by doing a mole balance around a differential volume, right? Differential volume of the reactor. There is another approach to derive the design equation, and that is by differentiating the general mole balance equation with respect to volume V. Okay, so let's do that. So again, this is the plug flow reactor, and I apply the general mole balance equation on the whole reactor. Okay, in the whole reactor. So when I say input, it's indeed Fi naught, because this is the input now. Okay, this is the input. Okay, and this is the output. So we have the input Fi naught to the whole reactor, right? And minus output from the whole reactor plus the generation inside the whole reactor. So that's from 0 to V equals the accumulation in the whole reactor. Okay, and of course it's operated under steady state, so no accumulation. And now let's take the derivative. Okay, let's take the derivative, meaning let's take derivative with respect to volume. So d over dv for the left hand side, the same thing d over dv for the right hand side. And for the right hand side is very easy, it's 0, right? The derivative of 0 is 0, and the derivative of this side, let's see, we have dfi naught by dv minus dfi by dv plus, let's see what we have here. We have here a function. This is my function. Okay, This is my function, which is Ri. This function is first integrated with respect to v, and then it is derived with respect to v. So let's write it, no big deal. D over dv for the integration of Ri dv. Okay, tamam. So let's go back and see what is the derivative of fi naught with respect to v. In other words, is fi naught function of volume? If I cut this reactor to half, will the value of fi naught change? No, it will not, right? So because fi naught is not function of volume, so this is not function of volume when you take the derivative, so it goes to 0. Let's look at fi. This is the fi, right? This is the fi. Is fi function of volume? Yes, it is, because if I cut it to half, right, now we have the molecule stays for less time. That means fi here will be greater than fi here at the end. So fi is function of volume. The bigger the reactor, the lower fi it is. If fi was a reactant, right? If I was a product, then the bigger the reactor, the more product you have. So fi is function of the volume of reactor, so that is stays as is. Okay, let's take again this term, and here we have the function Ri. So again, first thing of integrating with respect to volume, then I'm deriving it with respect to volume, correct? So it stays as is, stays the function as is, because the function is first integrated with respect to v, then derived again with respect to v. So stays the function as is and equals to 0. Again, I can rewrite it. That will be as dfi by dv equals Ri. Again, the same equation that we have derived using the other approach. That's the design equation of a plug flow reactor. Okay, so now we have both approaches that we have used, and they all lead to the same equation, that is this equation. So now we have the differential form, right? This is the differential form. If I want to find the volume necessary to reduce the entering molar flow rate from Fa naught to the exit molar flow rate Fa, then that means I have to integrate, correct? So I have to integrate, meaning I will rewrite this equation, I'll rewrite it, okay, as dFA divided by Ra equals dV, and then I integrate from 0 to V, and at volume 0 I have Fa equals Fa naught, at volume V I have Fa. So the integration is from Fa naught to Fa. Okay, and here we go. Okay, so now we have the differential form of plug flow reactor mole balance or design equation, and now this is the integral form of the plug flow reactor mole balance or design equation. If we solve this, then we can find if A as a function of V, okay, or we can do the same equation, we can write the same equation, but for B, if B is a product. So let's take this equation, A goes to B. You can write the design equation for B. Remember, the design equation was dFi by dV equals Ri. So I can write it as d dFB by dV equals Rb, and then I can solve it, and I get FB versus volume. So if A is the reactant, you can see that if A is decreasing as we go down the length of the reactor, okay, and here if B, which is a product, B is a product, the FB is increasing as we go down the length of the reactor. طيب, let's go to packed bed reactor. A packed bed reactor, still it's a tubular reactor. However, it's packed. Let's take this segment in the middle and peel the walls, okay, and we can see that it is packed with catalyst particles. Do you see the catalyst particle? It's packed with a catalyst particle because I want to catalyze my reaction. The fluid-solid heterogeneous reaction. So there is a heterogeneous reaction that's occurring between the fluid, whether it was a gas or liquid entering the reactor, and the solid here. This is the solid, right? This is the catalyst. This reaction takes place on the surface of the catalyst. So it occurs on the surface of the catalyst. Consequently, the reaction rate is based on the mass of solid catalyst, W, rather than the reactor volume, because now I care more about the catalyst than the volume of the reactor. Okay, therefore I base my calculation on how much catalyst I have, W. The rate of reaction of a substance A is therefore defined as minus Ra prime. Remember, we talked about this, minus Ra prime. Has a unit of mole A reacted per second per gram of catalyst. The mass of solid catalyst is used because the amount of the catalyst is what is important to the rate of product formation. Okay, how do you derive the design equation? Well, the same thing as you did for the plug flow reactor, and you can use either approach. However, now it will be dFA over dW. So it's not over dV, it will be over dW. And the rate will not be Ra, it will be Ra prime. Again, this is the differential form, and this is the integral form. Okay, let's look how a packed bed reactor looks like. Okay, so we explained this already, and let's look at this setup. This setup here, the gas, the reactant, flows from the bottom, and there is a distributor. It will distribute the flow over many pipes, many tubes, right? Many tubes. And these tubes are enclosed in a shell, in a bigger tank, right? So it looks like a tube and shell heat exchanger, right? It's like a tube and shell, or shell and tube heat exchanger. Okay, and of course, if you need to control the temperature, you can use the shell for that. So you flow a coolant here, and the coolant flows this direction. Why this direction? Because I have baffles, right? I have baffles, just like the heat exchanger, shell and tube heat exchanger, just like that. Okay, but as you can see, each tube is filled with catalyst. Or I could have the whole tank, the whole tube, the whole cylindrical tube, which is large. Okay, this guy. Okay, the whole shell or the whole tank or the whole cylindrical tube with a large diameter packed with the catalyst particle. So these are some of the schematic diagrams shown for plug flow reactor. This is some of the setup schemes of the plug flow reactors. Okay, great. So we stop here, and in the second segment we're gonna have an example to solve to show how to design a tubular reactor. See you soon.